In this section, we're going to start by talking about dependent events and move into talking about conditional probability. So dependent events are events whose outcomes do affect the probability of one another. So knowing that one event has happened might change your opinion about the likelihood of the next event happening. Like you've got some additional information now, and that might change the probability that the second event will actually occur. You move this out of the way here. Okay. So here's our first example. It says, in a pharmaceutical research study, half of a group of 500 patients suffering from chronic headaches were given a new pain-killing drug, and the other half were given a placebo. The results are shown in the table below. What is the probability that a random patient felt better? Okay, so what's important to note when they ask this is the out of is the total number of patients. So on this one, in this particular example, the denominator is going to be 500. And for the numerator, we want the felt better. So how many felt better out of the total amount of patients? So it looks like a total of 300 people felt better out of the 500 people total. So that's a 3/5 probability, or 60%. So 60% of the people felt better. What is the probability that a random patient felt better given that he or she has received the drug? So now we're only interested in the given the drug row because we have that information up front. So what that's going to do is it's going to change our values a little bit. If they've been given the drug for sure, then my new denominator now is 250 because the other people aren't even included in this question. We know that they received the drug. Now, what's the probability that a random patient felt better in this case? Well, it can only be the 183 now because, again, we're stuck in that given the drug row. So if we divide that out, let's see, 183 divided by 250 is about 0.732 or 73.2%. Okay, what is the probability that a random patient received the placebo given that he or she felt no better? Okay, so now we're given the information up front that they did not feel better. So now we're locked into this felt no better column, making our total that we take this out of is 200. And what's the probability that they received the placebo in this scenario? So let's see, how many received the placebo? There were 133 out of the 200 who received the placebo. And if we divide that out, I wish my zero button worked all the time. So that is 0.665 or 66.5%. So it says, notice that being given that extra information changes the total outcomes that you use, and it also ends up changing the numerator that you use as well. So this leads us to the idea of conditional probability. Conditional probability says the measure of the probability of an event E occurring given that another event F has already occurred is denoted by the following notation. So it's P parentheses E, then a straight vertical line F. And you read that as the probability of E given F. So that vertical line is read given. There's a formula for conditional probabilities. So the probability of E given F is equal to the probability of the intersection of E and F over the probability of F. So that one, the back probability of the E given F, that back one, the one that you're given, becomes your denominator. You can also take this formula and rewrite it to the following formulas. So basically what's happening here is they're multiplying by the probability of f, let's say, on both sides here to get rid of that denominator. So that gives us this formula right here. That if we take the probability of f times the probability of E given f, we would have the probability of the intersection. You can reverse that the other direction. What if it was f given E? So what if these two were reversed? Well, all that does is reverse the single probability there in that multiplication. So what this does is give us a new formula for all and probabilities. So I want you to recall that we did have a formula already for an and probability where we could take the two probabilities and multiply them together, but that was only true if E and F were independent. It was a very specific case. We had to know we had independent events, and then we know we can find the probability of the intersection by multiplying probability of E times probability of F. But these now work for any two events. We don't have to know independence or not for these to hold. But what it does lead us to is a little bit more information about independent events. So if E and F are in fact independent, then what that would mean is that the probability of E is equal to, this should be a P right here, is equal to the probability of E given F, and the probability of F is equal to the probability of F given E. So notice what that looks like there. Each of these match the front. The probability of F equals the probability of F given E. So what that's saying is that given this additional information does not change the probabilities. So given new info doesn't change the probabilities. So that is, again, what independent events mean. It means that the knowledge of this other event happening doesn't matter. It doesn't change the probability of the initial event. Okay, so now we've got all kinds of formulas that we can rely on. We've got general intersections, these two, that can be applied here only for independent events. So let's do one example to kind of follow up on these new probability formulas that we've got. So this is in a large survey of its customers, a nationwide retail store found that 20% made major purchases, denoted with an M, 48% had a charge account, noted with a C, and 12% fell into both categories. What is the probability that A, a customer has a charge account given that they made a major purchase? Okay, so let's write out what that looks like in symbols. That would be the probability of C given M. What's the probability that they have a charge account given that they made a major purchase? Okay, so if we go up and we apply our original, we're going to apply this formula right here for conditional probability. So we have to find the intersection over that second given that probability. So let's see, this is the probability of C intersect M over the probability of M. So the probability of the intersection is 12% or 0.12. We'll put that on the top. And the probability of M is 20%. That's M, so 0.20 goes on the bottom. So that's the same thing as 12 out of 20, which reduces to 3/5 or 60%. What's the probability that a customer makes a major purchase given that they have a charge account? Okay, so what if we reverse it? What if we say, what's the probability of M given C? Well, the definition, the formula says I have to take the probability of the intersection, on the top over the probability of the given that part, which in this case is C now. So the numerator stays the same, 0.12, but the denominator now changes to a 0.48. So that's 12 over 48, which reduces to 1/4, or 25%. So an interesting bit that we learn from this problem is that the order of the given that's, the order of the conditional probabilities matters. When you reverse which one given the other one, if you take that in the opposite direction, you are not necessarily going to get the same answer because those denominators change.